Alright, let's dive into the fascinating world of fossils and explore the process of fossilization. This incredible natural process allows us to catch a glimpse of the ancient past by preserving the remains of organisms in rock. Fossilization involves several key stages. The first stage is decay. When an organism dies, its soft tissues begin to decay and break down due to the action of bacteria, fungi, and other decomposers. However, some parts of the organism, like bones, teeth, or shells, are more resistant to decay and may persist for a longer time. Next comes sedimentation. In order for a fossil to form, the remains of the organism need to be buried by sediment, such as sand, mud, or silt. This can happen through various processes like river deposition, landslides, or volcanic eruptions. The faster the remains are buried, the better their chances of being preserved as a fossil. The third stage is mineralization. Over time, as more and more sediment accumulates on top of the buried remains, pressure and heat increase. This encourages the process of mineralization, in which the original organic material of the remains is replaced by minerals from the surrounding sediment. This creates a stable, mineralized replica of the original organism structure. Finally, we have the preservation of the organism's remains in rock. As the layers of sediment continue to accumulate and harden, they eventually form sedimentary rock. The mineralized remains of the organism are now preserved within this rock, essentially immortalizing them as a fossil. It's important to note that the fossilization process is quite rare and requires a unique set of circumstances to occur. Many factors can influence whether or not an organism becomes a fossil, such as its habitat, size, and the environmental conditions at the time of death. However, when the right conditions are met, the result is a fascinating window into Earth's history. Now that we've discussed the process of fossilization, let's move on to the different types of fossils that can be formed. There are three main categories: body fossils, trace fossils, and chemical fossils. Each of these types provides unique information about past organisms and their environments. First up, we have body fossils. These are the most well-known type of fossil and include preserved remains of an organism's hard parts, such as bones, teeth, and shells. Body fossils can tell us a lot about the structure and appearance of ancient organisms, as well as their age and distribution across different geographical regions. Next, let's talk about trace fossils. These are not the remains of the organism itself, but rather the evidence of its activities or behavior. Examples of trace fossils include footprints, burrows, and even fossilized feces. Trace fossils can provide valuable information about how ancient organisms interacted with their environment, their hunting or foraging strategies, and their social behavior. Lastly, we have chemical fossils, which are also known as molecular fossils or biomarkers. These fossils consist of organic molecules that were once part of an organism's tissues or cells. Over time, these molecules are altered by chemical processes but still retain some of their original characteristics, allowing scientists to identify the presence of specific organisms in the fossil record. Chemical fossils can help us learn about the composition of ancient ecosystems and how they might have changed over time. So as you can see, each type of fossil offers unique insights into the lives of ancient organisms and the environments they inhabited. By studying these different types of fossils, scientists can piece together a more complete picture of the Earth's history and the evolution of life on our planet. Let's now explore the role of environmental factors in the preservation of fossils and how they can impact the quality of the fossil record. Factors such as sedimentation, burial, and temperature play a crucial role in determining whether an organism's remains will become a fossil or not. First, let's discuss sedimentation. As we mentioned earlier, the burial of an organism's remains by sediment is a key step in the fossilization process. The type and rate of sedimentation can greatly influence the preservation of fossils. For example, in environments with slow sedimentation rates, like a calm lake, there is a higher possibility for delicate structures to be preserved. On the other hand, in environments with high sedimentation rates, like a river delta, fossils may be less detailed due to the rapid burial and compression of the remains. Burial depth is another important factor in fossil preservation. The deeper an organism's remains are buried, the more protected they are from disturbances such as erosion or scavengers. However, deeper burial also subjects fossils to greater pressure and temperature, which can lead to more extensive mineralization and changes in the original structure of the remains. Temperature plays a significant role in the preservation of fossils as well. Lower temperatures can slow down the decay process, increasing the chances of preservation. For example, fossils found in permafrost regions are often exceptionally well preserved because the cold temperatures have slowed decay. In contrast, higher temperatures can speed up decay and reduce the likelihood of fossilization. Additionally, other environmental factors such as water chemistry, oxygen levels, and the presence of scavengers can also impact fossil preservation. For instance, anoxic, oxygen-poor environments can help preserve fossils as they limit the activity of decomposers that break down organic material. In summary, various environmental factors can greatly influence the preservation of fossils and the quality of the fossil record. By understanding these factors, scientists can better interpret the information that fossils provide about Earth's history and the organisms that once inhabited our planet. Now let's delve into the importance of fossils in understanding Earth's history. Fossils are invaluable tools for scientists because they provide crucial information about the past, including the study of evolution, extinction events, and changes in climate and ecosystems over time. First, fossils are essential for understanding the evolution of life on Earth. By studying the morphological changes in fossils over time and across different geographical regions, scientists can trace the evolutionary relationships between different species. This helps us understand how different organisms have adapted to their environments, developed new features, and diversified into countless forms over millions of years. Second, fossils provide insights into extinction events that have occurred throughout Earth's history. By examining the fossil record, scientists can identify periods when large numbers of species disappeared from the planet, allowing them to study the causes and consequences of these mass extinctions. Some well-known examples include the extinction of the dinosaurs around 65 million years ago and the Permian-Triassic extinction event, which wiped out around 90% of marine species and 70% of terrestrial species around 250 million years ago. Third, fossils help us understand changes in climate and ecosystems over time. By studying the distribution of different types of fossils and the sediments they are preserved in, scientists can reconstruct past environments and assess how they have changed over millions of years. This information can help us understand how climate change has affected life on Earth in the past and provide valuable insights into how modern ecosystems might respond to ongoing and future climate change. In summary, fossils play a crucial role in our understanding of Earth's history. They provide a window into the past, allowing us to study the evolution of life, the causes and consequences of extinction events, and the changes in climate and ecosystems over time. This knowledge helps us appreciate the incredible diversity of life on our planet and provides important context for addressing contemporary environmental challenges. In this final section, we'll examine the methods used by paleontologists to study fossils. These experts employ a variety of techniques, including excavation, dating methods, and the application of modern technology to analyze fossil material and uncover the secrets of Earth's history. First, let's talk about excavation techniques. When paleontologists discover a potential fossil site, they carefully remove the surrounding rock and sediment to expose the fossils. This process, called excavation, requires a combination of patience, precision, and specialized tools, such as brushes, chisels, and even dental instruments. It's important to minimize damage to the fossils during excavation, as they can be quite fragile. Once fossils have been excavated, paleontologists use various dating methods to determine their age. One common method is relative dating, which involves comparing the age of a fossil to the ages of other fossils and rock layers in the same area. This can help establish a chronological sequence of events in Earth's history. Another method is radiometric dating, which involves measuring the decay of radioactive isotopes within a fossil or the surrounding rock. This technique can provide more precise age estimates for fossils, sometimes down to the merest 1,000 years. Modern technology also plays a significant role in the study of fossils. For example, computed tomography CT scans and X-rays can be used to create detailed, three-dimensional images of fossils without damaging them. This allows paleontologists to study the internal structures of fossils, which can provide valuable insights into the anatomy and physiology of ancient organisms. Additionally, techniques such as stable isotope analysis and DNA sequencing can be used to study the chemical composition of fossils, revealing information about ancient diets, environments, and evolutionary relations. In conclusion, the methods used by paleontologists to study fossils are diverse and constantly evolving. By combining traditional excavation techniques with cutting-edge technology, these experts can unlock the secrets of Earth's history and deepen our understanding of the incredible story of life on our planet.